talk about in the chapter. First, we will talk about something called digital modulation, and the other is analog modulation. Do you know what is modulation? Did you ever hear this word modulation? Yes. Okay. What does it mean?
Change.
Change. Okay.
That can be changed.
Where, in which course did you study modulation? Or where did you hear this word?
From the previous
Signal analysis?
Yeah, no.
Oh, in this one.
Advanced logic design.
But before this course?
Advanced logic design. Yeah.
Advanced logic design. Okay. So did you talk about signal, or what did you talk about modulation?
I said module.
No, module is different.
From
It's not
modulation.
module. No. Modulation is something different and module is different. They are two different things. Okay. There are two types of modulations, mainly digital modulation and analog modulation, right? You know what is the meaning of digital, this word, and you know what is the meaning of analog. Okay. What is digital modulation? Converting digital data into an analog signal, right? I have been saying this to you, that you have bits, zeros and ones, and you have to transmit them. So how do you send the bits? You convert them into signals, right? So we convert them into signals using the techniques in chapter 4, line coding, Manchester coding, or NRZI, or whatever. We talk about different types of square waves and all that. So that way you convert your bits into a signal. After that, this is a second operation where you convert that one into an analog signal. Okay, we will see that why we do that, why we are adding an extra operation. In the case of analog modulation, you already have an analog signal and you are converting it into another analog signal, right? And again, the question arises that I already have an analog signal, I can send it as is, why do I need to convert it into another signal?
Maybe because of the bandwidth.
Maybe, exactly. One of the main reasons is the bandwidth, right? Now we will see that what are the different reasons of converting a signal into analog signal, right? Now first of all, what is modulation? Modulation is the process of changing one of the properties of an analog signal based on the information to be transferred, right? Again, what is modulation? It is the process of, shall I open the door? Is it? It's getting cold, right? But it will not stay. I don't know how you guys stop it. Okay. It is a process of changing one of the properties of an analog signal. So you already have an analog signal, right? And you are changing one of its properties. Okay. I give you an example to make it understand. Let's suppose you have some big, heavy boxes, okay, that you want to take from Makkah to Jeddah. What will you do? You will hire a truck or something, right? And you will put that stuff on that truck, and that truck will take, right?
Yes.
So the data that you are sending is that boxes, okay? And that truck is the signal that he's talking about, analog signal, right? So just like you are putting your boxes on the truck so that the truck can take them from this city to another city, similarly you put your information in an analog signal so that the analog signal can take your information, right? There is a reason for doing that, but it is you can consider this analog signal as a truck on which you are putting your information, right? So you can put your boxes either at the back of the truck or on the rooftop of the truck, for example, or inside the truck. There are different ways of putting your information, your boxes. Similarly here, it is the process of changing one of the properties of an analog. You can put the information in one of the parameters of the signal. What does it mean by? For example, let's take a sine wave. Let's suppose I'm using a sine wave, which is a truck, right? The sine wave is a truck, assume. Okay. So there are three properties of a sine wave, right? Amplitude, frequency, and phase. If I give you the amplitude, frequency, and phase of a sine wave, you can right away draw the sine wave, right? You don't need any other information.
Yes.
When we change any one of these properties, we create a different version of that, right? Now, what we do is, we put the information that we have on this sine wave by either changing the amplitude or the frequency or the phase. Okay? It is like you are putting the boxes at the back of the truck. So, for example, we are putting the information in the amplitude of the sine wave. We are putting the boxes at the rooftop of that truck. It is like you are putting your information in the frequency of that sign. And phase, for example, you are putting your boxes inside the truck, okay, it is like putting your information in the phase of that sign, right? So the idea is that you have a sine wave, it has amplitude, it has frequency, it has phase. So you take your information that you are sending, either bits or analog, and you either put it in the amplitude of that signal, or you put in the frequency of that signal, or you put in the phase of that signal, right? You will see the details how we do that. So this way, we are going to have 4 different types of modulation schemes for digital signals. Okay, right now we are talking about digital signals. One is called amplitude shift key, ASK. This is when you put the information in the amplitude of the sine. Then there is called frequency shift key, when you put your information in the frequency of the analog signal. Then phase shift key, when you put the information in the phase of the sine wave, and there is something called quadrature amplitude modulation. In this case, we are putting the information in both phase and amplitude both together. Okay, this is called quadrature amplitude modulation. Okay. Now the question comes then to why we are modulating. What is the reason? We already have a signal, we should send it. One of the reasons is modulation allows us to send a signal over a band pass frequency, as he said. If every signal gets its own frequency range, then we can transmit multiple signals simultaneously. Okay, exam one, this word was in exam. Some students had problem in understanding. Over a single channel, all using different frequencies. Basically, what he's saying is this. You have a signal, okay, that you generate. When you generate a signal, most of the time its frequency is starting from 0 and it is going up to some frequency that's called f. Okay, this is the signal that you want to send. Now the channel that you have, either fiber optic or cable or wireless, let's suppose you have a channel and its bandwidth is like this. Okay, and you have to send this signal. Now let's suppose this F1 is less than F1, F8, right? So this means this signal is somewhere here, right? Will it pass through this channel? No. So you have to shift its frequency so that it falls in this range, F8, right? Otherwise you cannot send it.
Yes.
So this is one of the reasons that you use modulation to shift the frequency of your signal from this to this one. So whatever range you want, right? Another reason is that, for example, you want to send more than one signal, and you only have one channel, and you want to send 4 signals, right? So you have one signal with this frequency, one signal with this frequency, and one signal with this frequency, right? Or let's take an example like this. Let's suppose you have one signal whose frequency range is 0 to f1, right? You have another signal, let's suppose, whose frequency range is from 0 to, let's suppose, f2. Another signal whose frequency range is from 0 to, let's suppose, some f3. And you want to send these 3 signals through this channel, right? At the same time, what would you do? You will shift its frequency so that it falls in this range, right? Then you will shift this guy such that his frequency starts from here and ends here. This is the second. And for the third one, you will shift its frequency so that it falls in this. So you can send all 3 signals to the same channel without any problem. This is what he's saying. Now if you read it, it will make more sense. Modulation allows us to send a signal over a band pass frequency range. This is the band pass frequency range through which you want to send your signal. If every signal gets its own frequency range, means this signal gets its range, this is the range of second signal, and this is the range of the third signal. Then we can transmit multiple signals at the same time. Simultaneously means at the same time over a single channel. This single channel, all using different frequency ranges. So one signal uses this range, second uses this range, and third uses this range. This way you can send multiple signals through the same channel. Is this clear?
Yes.
Any questions?
Doctor,
Yes.
the channel have ultimate signal ticket or
Again?
the channel
Uh-huh.
have infinite for signal?
No, it's not infinite. The
No,
channel will always...
yes, they have infinite or have
No,
limit.
it is limited. That's why. This is the reason. If it had infinite range, then there was no problem. The problem is that all the channels have a finite range. They have a fixed range. Okay, especially in wireless, as I told you, the wireless channel is very expensive. Okay, so they allocate the bandwidth, so you have to stay within that bandwidth. Okay. Now let's move forward. The second reason is a low frequency signal needs a huge antenna. Okay? Because, why? Because in order to be efficient, the antenna needs to be about 1/10 the length of the wave. Modulation shifts the baseband signal up to a much higher frequency, which has much smaller wavelengths and allows the use of a much smaller antenna. This is the reason that the antennas in your mobile phones, you cannot see them, right? They are inside and they're very small, okay? And this is the reason that they are small. You remember we did something about wavelength? There was a formula. Anyone remembers wavelength and frequency? What is the relationship?
Lambda.
Yeah.
Lambda is like
C over F equals C over F.
Lambda is equal to C over F. What does it mean? If the frequency is low, lambda is going to be high, because this is a constant, right? The frequency is low, lambda is high. And if the frequency is high, lambda is low. And lambda is what? Wavelength, right? Now read this. A low frequency signal needs a huge antenna. Why? The antenna has to be about 1/10 the length of the wavelength. So if your frequency is low, lambda is going to be high. And the 1/10 of that lambda is going to be high, right? So let's take an example. Let's suppose lambda is 100, okay? So this means the antenna size has to be 1/10 of 100, which is 10, right? If lambda becomes 10,000, so the antenna length will be 1,000. 1/10, right? 1/10 of 1,000 is 1,000, right? Sorry, 1/10 of 10,000 is 1,000, right? Now, if I decrease lambda, if I make lambda as 10, so how much is the length of the antenna?
1.
1, right? So this means if I keep on increasing f, lambda will keep on decreasing, and therefore the length of the antenna will also decrease. So that's why I have to have my signal of a much higher frequency, so that when this is high, this is low, and the size of antenna is also low, right? Is that clear?
Yes.
Okay. This is the second reason that we need to modulate. So what we do, we modulate to a higher frequency so that wavelength becomes low and we need to use a smaller antenna. Third reason, low frequency signals get attenuated. You know what is the meaning of attenuation, right? Losing energy. Low frequency signals get attenuated in space, while high frequency signals do not get attenuated in space as fast as low frequency. So if you have a signal with low frequency, the chances of attenuation are much higher as compared to a signal whose frequency is high, right?
Conductor noise. The frequency is higher, your signal is much better dealing with noise.
Yeah, depends upon which type of noise you're talking about. Yes. So low frequency signals get attenuated in space, while high frequency do not get attenuated in space as fast as low frequency. And the high frequency signals can travel along long distance. Low frequency signals cannot travel long distance. Thus, if low frequency is used for some application, then its strength will be less, resulting poor reception. So if you send your signal at a low frequency, you are going to face these problems. Okay. So these are the reasons that we try to modulate our signal. And you can see that the main thing in this modulation, we are trying to shift the frequency of your signal from some low frequency to a high. Okay, now this is a diagram. Well, the book calls this modulation as digital to analog conversion, but strictly speaking, it is not D to A conversion. It is basically analog modulation, digital modulation. So let's suppose you have this digital data that you want to send. Okay. So first you will convert it into some Manchester or whatever. Then you do modulation. After modulation, your signal becomes like this, an analog signal. Okay. It travels through the link. At the receiver, there is an opposite of modulator, which is demodulated. Okay. It demodulates and you get back your digital data. Right? This is a. Now, what are the different types of digital modulation? I just told you. There is amplitude shift keying, frequency shift keying, and phase shift keying. Right? This, to be strictly speaking, this is actually digital modulation. This is a better word for this. But this book is using this term, the digital analog converter. Strictly speaking, this should be digital modulation. So this is ASK, FSK, and PSK. And what is QAM? You can see that it is a combination of PSK and ASK. Right?
Yes.
Okay. Carrier signal. Okay. Our truck. This is the truck on which you are going to put your information. Okay. So what is a carrier signal? It is a high frequency sine wave that is used to carry information. Right? So it is basically a big truck that will carry your boxes. Okay, so carrier signal is a high frequency sine wave that will carry your information. The carrier can carry the information by three methods. By varying the amplitude, you come late and then you want to leave as well. The carrier can carry the information by three methods. By varying the amplitude of the carrier, by varying the frequency of the carrier, and by varying the phase of the carrier. So as I said, that if you have the truck, either you can put it at the back of the truck, for example, or at the roof of the truck with boxes, or inside the truck.
That's right.
This way there are three different methods of modulating your signal. Okay, is it clear until this point? Any questions, any confusions? Okay, so let's take all of them one by one. Let's take the first one. When you vary the amplitude, the modulation is called amplitude shift key. What happens in amplitude shift key? In amplitude shift key, the amplitude of the carrier signal is varied. Varied means changed. It creates signal alerts. Both frequency and phase remain constant while the amplitude changes. So when you use amplitude shift key, only the amplitude will change, other things will not change. For example, now this example will make things clear. Let us suppose that we have this digital data, 1, 0, 1, 1, 0, and so on. Okay. So what we say that we are using amplitude shift key. That means, first of all, we should have a carrier signal. So the carrier signal is this one, a high frequency sine. And I want to put my information in the amplitude of that carrier signal, right? How do I do that? For example, if I have to send a bit 1, I will send the signal with full amplitude. If I have to send a bit 0, I will make the amplitude 0. Again a 1 comes, I will again send the same signal with full amplitude. Another 1 has come, I continue sending the signal with full amplitude. And when a 0 comes, I send the signal with 0 amplitude. Right? And you can see the frequency is not changing for the signal throughout. And the phase is also not changing. The phase is 0 here, phase is 0 here, phase is supposed to be 0, and everywhere the phase is 0. Frequency is the same. So in amplitude shift key, we are only changing the amplitude. We are putting the information in it. When the signal is at full amplitude, this means it is carrying a bit 1. If the signal is 0 amplitude, it is carrying bit 0. Right? So, and the frequency and phase, they don't change. They remain the same. This is called amplitude shift key, and we call it binary because we are sending one bit at a time. When you send one bit at a time, this is called binary. And when you send more than that, then there are different names. Okay, so if you have these 5 bits, then of course bit rate is 5 because in this time is 1 second, right? And since you are sending one signal element in 1 bit, the baud rate is also 5. Right? Is that clear?
Doctor, the signal infinity or stop?
No, it depends upon your data.
No.
If the data keeps on coming, your signal will keep on going.
Okay, but the bit 0, it's zero signal.
Yes, zero signal.
How the receiver don't he know stop the signal?
Yeah, because when the receiver receives something like this, a 5-volt signal, he knows it is 1. And when then he doesn't receive anything, he would think that this is a bit 0.
Okay.
But in reality, in practical terms, we avoid sending zero signal. We try to send something because because of noise, he might be receiving something. He may mistaken. But just to understand the concept, so that you know that in amplitude we are changing the amplitude, and this is a good example to show that. That's why we show a zero signal. But it's
Yeah.
not a good practice to send a zero signal for a 100 signal.
Yes.
Yes.
How it's look like the original signal for this one?
Original signal for this.
Yeah.
Yeah. He's saying how the carrier signal looks like, right? On which you are putting the information. The carrier signal should look like something like this. This is your carrier signal, right? So what happens then? This is your carrier signal. Actually, I have answer to your question on the next slide. Let me show the next slide. This is your information, bits, okay? And this is your carrier signal, right? So this is the hardware that you use. So there is an oscillator that generates the carrier signal of frequency FC, okay? And this is your bits, right? In the form of Manchester or differential Manchester, whatever you use. It gets multiplied with this and you get this, right? So you see here, these are the bits and this is the carrier. When it gets multiplied, automatically you get this signal. So for 1, you see that the signal is going as is. For 0, it automatically gets 0. For 1, again, it keeps on going like that, and for 0, it is like that. Right?
Doctor,
Yes.
you said that modulation is the change from digital to analog, right?
Yeah, modulation is for, see, there are 2 types of modulation. This modulation, this is called digital modulation, in which you are changing your digital signal or digital data into an analog signal.
Okay. And what is that before?
That is called line coding, which is in what happens in Manchester and differential Manchester, that you have bits 0, 1, 0. Now I have these numbers. How do I send them? This is not a signal. I need a signal. Okay. So for that, I convert it into differential Manchester or Manchester whatever. And when I convert, I make sure that they have certain properties. No DC component, synchronization, all those things that we talked about, right? You can use that signal as is. You can send it. But the problem with that signal is that it is not in the frequency range that we want, right? Because our channel is over here, my signal is over here, so I have to move it into that channel. That's why then I have to do this extra operation where I change my digital signal into an analog signal, right? Okay, so let's go back. So this is what we talked about. Now, what is the bandwidth of the signal? Because bandwidth is very important. Whenever you do any operation on a signal, you have to check its bandwidth. Is it taking more bandwidth or less bandwidth? So for this case, the bandwidth of ASK is B is equal to 1 plus D multiplied by S. Here you know B is bandwidth. You know S is
Second. Time.
S is
Second?
baud rate. S is baud rate. Signal rate. S is signal rate or baud rate. Okay? And D is a constant which depends upon the modulation scheme, and it's the value will be between 0 and 1. Okay? They will tell you what is the value. So therefore, if B is 0, the bandwidth will be the same as baud rate, right? B will be equal to S. And if D is equal to 1, which is the maximum value of T, then the bandwidth will be 2S. So this means that for ASK, the bandwidth will range from S to 2S. It will be either minimum it will be S and maximum it will be 2S, depending upon the value of T. And it looks something like this. you can see that since R is equal to 1, why R is 1? Why R is 1? Someone said something. Why R is 1? No. We did it in the last chapter. S is equal to 1 over R into N. Right? R tells you R is the ratio of the data element to the signal element. So because you are sending one bit in one signal element, so that is why R is equal to 1. If you are sending 2 bits in one data element, then R is equal to 2. So here, since it is binary, you are sending 1 bit at a time, so R is equal to 1. That's why S and N are same. Right? S is equal to 1 by R into N. And then P is equal to 1 plus U. So this is something like this. This is how you show the band. That this is your carrier frequency, and you take some space here, some space here in the spectrum. All right, any questions? Okay. Now implementation, I just talked about it. This is how you can implement it. Now let's take an example. We have an available bandwidth of 100 kilohertz, okay, which spans from 200 to 300 kilo. What's the meaning of spans? 100 kilohertz, it spans from 200 to 300 kilohertz. Or do you understand this first sentence? What is he trying to say?
Yeah, it's start from 200.
Yeah, exactly. It means that the bandwidth starts from 200 and goes up to 300. So it starts from 200, goes up to 300. So the bandwidth is 300 minus 200, which is 1. That's what he's saying. What are the carrier frequency and the bit rate if we modulated our data by using ASK with D equal to 1, right? So the bandwidth is 100 kilohertz, right? And he's saying, what are the carrier frequency and the bit rate if we modulated our data by using ASK? So he gave you the bandwidth and he gave you D. So what is he asking?
Yes.
He's asking for bit rate, okay, which is
Yes.
N, right? And he's asking for carrier frequency, which is FC. Okay, now this FC is easy. Why is it easy? Remember the diagram that I showed you in the 2 slides before, like this, and this was FC, right? So FC is always in the middle of the band. So it starts from 200 and goes up to 300, right? This is what it shows. So what is FC?
250.
250. 250, right?
Yes.
So FC we know. Now B is given. How can I find N? We know the formula. B is equal to 1 plus
B.
T into S, right? P is given, which is 100. B is given, which is 1, so it becomes 1 plus 1. And S we have to find out, right?
S
And
equal N.
he's asking for N. So I can replace S by
N.
N. Why I can replace by N? Because this is a binary, right? S and N are same. So 100 is equal to 2N. So N is equal to 50. What are the units? Units of this 50. Bits per second?
Kilobit.
Kilobits per second. Yes. Kilobits per second. Because this 100 is in kilohertz. Okay, the solution is here in the slide. I'll just show you that solution. Okay, here is the solution, and he told me that FC is 250. Okay, bandwidth of a full duplex ASK. Okay. If you are using a full duplex system, then you need a complete bandwidth for both the directions. What does it mean? It means that you have one modulation for one side and another modulation for another side, right? So this is for example, left to right, and this is from right to left for full duplex. Okay. So this is an example where 50 kilohertz bandwidth is reserved for one direction and 50 kilohertz for the other direction. Okay? And that's what he's saying in this. He's explaining all this. Okay, whatever I just said. Okay, now let's move to another one. We talked about amplitude shift keying. Okay, we said that there are three types: amplitude shift keying, frequency shift keying, and phase shift keying. Okay, so we talked about amplitude shift keying. Now we talk about frequency shift keying. Frequency of the carrier signal is varied. You know what's the meaning of varied? Changed. So we change the frequency of the carrier to represent data. Frequency of the modulated signal is constant for the duration of one signal element. I will show you how it is done. Frequency changes for the next signal element if the data element changes. Okay. Both peak amplitude and phase remain constant. Okay. And this is how it is done. If a bit 1 is coming, I am sending the signal with this frequency, right? When a bit 0 comes, can you see that the frequency has changed? It has become smaller, lower, right? But during this duration, the frequency is constant. When a 1 comes, it again changes to the same, right? Another 1 has come, so it continues with that higher frequency. And when a 0 comes, it again becomes smaller, right? So it's very easy. The idea is simple, that if a bit 1 comes, I send the signal with a frequency, let's suppose 100 kilohertz. When a bit 0 comes, I send the signal with a frequency, let's suppose 50 kilohertz. Right? So for 1, I am using a high frequency, and for 0, I am using a low frequency. And this is how it looks like. You can see that it is different than the ASK, the bandwidth. This is for frequency F1, right? Let's suppose for bit 0, and this is a higher frequency, so let's suppose this is for bit 1. This bandwidth is S into 1 plus G, and this again S into 1 plus T. The difference between F1 and F2 is 2 delta F. So the formula is E is equal to 1 plus G. Well, this is the same as for ASK. You see plus 2 delta F is added, okay, to make sure take care of this. And R is 1 because we are talking about binary. R is 1. So S and N are also equal.
If he was using the one from previous amplitude shift key, and he was using two bandwidth, is it also plus 2 delta F?
If in ASK he is using 2 bandwidth for duplex,
yes,
right? So for duplex, then it is something similar, yes. So in that case, one will be used for one direction and the other will be used for the other direction. Yes, good observation. What he's saying that in ASK, when we use duplex, I showed you a diagram over here, this one. So we said that this is still ASK, but since we are talking about duplex, so this is in one direction, this is in the other direction. And what I just showed you for the frequency shift key, the diagram is quite similar, right? The only thing is that in that case, you are changing the frequency. Here, the frequency is constant, only the amplitude is changed, right? But you're using 2 different frequencies. Okay, we have an available bandwidth of 100 kilohertz, which spans from same question. Okay, but now he's asking this for FSK. What should be the carrier frequency and the bit rate if you modulate our data by FSK where T is 1 and 2 delta F 50 kilohertz? It's very easy, right? You have the formula, you can put the values in the formula and find the answer. You know the bandwidth, okay? You know the formula. B is equal to 1 plus G into S plus 2 delta F. He gave you 2 delta F, he gave you D, he gave you B, you just have to find S, right? Just like this. Right, is it clear? Any questions? It's exactly the same as ASK. The only difference is the formula is different. Okay. Now we solve some problems. In all these problems, assume C is equal to 1. Remember that formula that you did in the last chapter, which is S is equal to C into 1 by R into N, right? This we did in the last chapter. Here he's saying assume C1 for all these problems. Okay, just use R and N to solve this problem. Let's take the first one. calculate the baud rate for the given bit rate. These the bit rates are given, modulation scheme is given, and he's asking you for the baud rate, right? So what is the baud rate for the first case? Come on, do you need a calculator for this?
No, it will be 2000.
Yes.
Because it's equivalent.
Yeah. R is 1. See, C is 1, R is 1. So S is equal to N. Plus. N is this, so S is this. The only difference is you write a BPS or S, you write baud. Right? Just like this. Yes.
This problem, how did we assume R is 1?
Because it is binary. We are sending one bit in one signal line. We are sending one bit at a time. Okay? Calculate the bit rate for the given baud rate, and now this is the other way around. He gave you baud rate and he's asking for bit rate. Right? So since it is binary, so it is going to be the same. The only difference is this is 1000 baud. In bit rate it will be 1000 bits per second, BPS. Right? Any questions? What is the number of bits per baud for the following techniques? Yeah. Now, part A. ASK with 4 different amplitudes. What is the meaning of this? ASK is with 4 different amplitudes. What is the meaning of this?
There is 4 combinations. Like 0, 0, 0,
Yeah.
1, 0, 1.
Exactly. So what he's saying here is ASK with 4 different amplitudes. What does it mean? That in this case we are using 2 bits at a time. Like this. The previous one, what we had was either 0 or 1, right? So for 0 we were sending a 0 volt signal, and for 1 we were sending a sine wave with full amplitude, right? This was the case which is called binary, right? Okay. Now here he's saying 4 amplitudes, 4 different amplitudes. Here, how many amplitudes do you have here? 2. For this one there is 0 volt, okay, and for this one let's suppose it is 5. Now he's saying 4 different amplitudes means that now I have 0, 0, 0, 1, 1, 0, and 1. I have 4. So that means that for 0, 0, I will be using some other voltage. Let's suppose I say I'm going to use minus 3 volts, not minus 3, whatever. So 4 different amplitudes means I'm using 2 bits at a time. Right? 4 different amplitudes means I'm using 2 bits at a time. So what is the number of bits per baud for this case? 2 bits per baud, right? It's an oral question, right? But if you want to make sure, then you can use that formula. R is equal to log L to the base 2, right? What is L? L is the number of levels that you need or the number of combinations that you have. So here I have 4. So R is equal to log of 4 to the base 2, which is 2. So R is 2, which means 2 bits per baud. Right? Similarly, this one, FSK with 8 different frequencies. What's the meaning of 8 frequencies? How many bits I'm using at a time? 3 bits, exactly. Not 4.
No,
that is 16. I'm using 3 bits at a time. For 3 bits, I have 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, all the way up to 1, 1, 1. So when I have 8 amplitude or 8 different frequencies, that means I'm using 3 bits at a time. Okay? And I have to use 8 different frequencies. And let's suppose F1, F2, F3, all the way up to F8. Right? Any questions? Okay. So this is also called, multi-level FSK. This one, the one with 8 different frequencies, it is multi-level FSK. Right? Multi-level means that It's not just 2, it could be 4, or it could be 8, or 16, or whatever. Now let's talk about phase shift. We talked about ASK, where we were putting the information in the amplitude of the signal. We talked about FSK, in which we were putting the information in the frequency of the carrier. Okay? And now we talk about the third case, which is phase shifting. Here we put the information in the phase of the carrier signal. Okay? So phase of the carrier signal is varied as a function of data bits. Right? So you change the phase based upon what bits have come. Both peak amplitude and frequency remain constant as the phase changes. Right? So in all three schemes, when you put the information in one of the properties, the other two remain same. Like this one. Let's suppose I am sending a bit 1. So for bit 1, I am using phase equal to 0 degrees. So you see here it starts from 0. Okay, so it goes like this, the way as before, and it stops. Now when the 0 comes, you see I am not starting from 0. What is the phase for this for bit 0? 180 degrees. 180 degrees, right? Why 180 degrees? Because
from 0 degrees.
you know this circuit, it starts from 0. Okay. How much is this? 90. And then you come back to 360. Right? So I have so many phases to be used. Where are you going? Yeah, you should first ask. Okay. So here it is 0. So what I'm doing, I'm using two phases because I have only 0 and 1. So one phase I choose this, and the other phase I choose this one. Right? It's not that you choose one over here and one over here. Right? We will see what's the reason. Okay. Whenever you can choose these two, or you can choose these two. And you can rotate it. Okay, you can use any, but they have to be exactly on the opposite sides, right? To minimize the errors. This is to minimize the errors. So, when the bit 1 comes, I send the carrier wave with phase 0. And when a bit 0 comes, you see here, I am sending the half of the cycle is missing. Right? Where is the half cycle? Because my phase has changed to 180. It goes until here, and then the 1 has come, so again it becomes 0. And the 1 comes, so it continues. 0 has come, so it again becomes 180, and so on. Right? So here I am using two phases. One is 0 and one is 180 degrees. And this is the bandwidth. You can see it's the same as for ASK. Now there is something called quadrature phase shift. Now this one, the one that we just talked about, this is binary phase shift. Okay. In short, it is also called BPSK. Binary phase shift key. Okay. If you have ASK which is binary, you can also call it BASK. Okay. Or for frequency, it is BFSK. So whenever there is binary, it is supposed to be one bit at a time. You know, in the questions or in the exam, if nothing is specified, that if I don't tell you how many bits I'm using, I just say, okay, there is a scheme phase shift key. So if it is not mentioned, that means it is binary, right? Like I give you an example so that you don't get confused. Like this one, if he does like this, he doesn't put binary here. Okay, so calculate the bit rate for the given baud rate and type of modulation. 1000 baud FSC. They didn't tell you anything. So this is binary. Okay. So what is quadrature shift key? Use 2 bits at a time in one signal element. We're talking about this especially because it is used a lot. QPSK is used a lot, so that's why we are talking about it specifically. Okay, so quadrature phase shift key, you are sending 2 bits at a time. Hence, there are 4 different phases instead of 2, right? I need 4 phases. Yeah? For example, the 4 phases could be 45, 135, 135. So what does it mean by that? Then you can either you can do this. You need 4 different phases because you are sending 2 bits at a time. So one phase could be this, one could be this, one could be this, and one could be this. Right? And as I said, these 4 you can rotate. What he's telling you is he's asking you to use this. This one, which is 45 degrees. Then this one, which is 135. Then he's asking you to use this one, which is minus 135. If you measure from here, if you measure from here, it is different. And this one is minus 45, right? So this is 45. This is 135. And this one, if I measure from here, this is minus 135 degrees. And this one is minus 45. Basically what he's saying that you send your waves with these phases. Like for example, there is a diagram here, it's not very good, but still it gives you some idea that he's starting it at a very kind of odd style, okay? Because the phase is minus 135. Here the phase is minus 45 for 1, 0. For 0, 1 the phase is 135 and for 1, 1 the phase is 45 degrees. It's not very accurate, but it conveys the concept. Right, any questions? Okay.
Clear.
Find the bandwidth for a signal transmitting at 12 megabits per second for QPSK. The value of D is equal to 0. Very easy question. What should I do?
Same.
See, you know the formula for the bandwidth.
Yeah.
The same
But
as
output
K.
is 1 plus 0, so the S will be well.
Yeah, here you made a mistake.
No,
Exactly.
R
That's
is
what,
2.
because it is QPSK, so here R is equal to 2. That's the difference. Right, is that clear? It is QPSK, so R is equal to 2, so that's why.
Here he didn't get a C.
Yeah, as I told you, assume C to be 1. The whole chapter C is 1. Now, concept of a constellation diagram. There is something called constellation diagram. So you see, whenever we want to show a signal, okay, like for example a sine wave you want to show, so you need to show on the diagram the amplitude and the phase and the frequency, right? So to make that job easy, there is something which is called constellation that very easily can show the signal. Okay. So this is how we show. What we do is, remember this is x-axis and this is y-axis. Okay. So we use vectors. Okay. This is a vector. The length of this vector is actually the amplitude of your signal. Right? If the amplitude is 5 volts, the length is going to be 5. Okay? If the amplitude is 3 volts, the length of this vector will be 3. This angle shows you the phase. Right? If your signal is with a 0 phase, then this line will be along the x-axis. If your signal has a phase of 90 degrees, the line will be over here. If your signal is 180 degrees out of phase, then it will be over here. And so on. Right? So instead of drawing the whole signal, we can just use these dots to represent our signals. Now this line, this part is called I component or in phase component, and this part of this is called quadrature phase component or Q component. See, X is the in-phase carrier and Y is the quadrature carrier. Because we are talking about the carrier signal. Now, let's take an example to see how it works. See, if you look at this diagram, this is constellation diagram for BASK, binary amplitude shift key. Now see here, for bit 0, I am sending this dot. And for bit 1, I am sending this dot. What does it mean? That to send bit 0, the amplitude of my signal is 0 and the phase is also 0. For sending bit 1, the amplitude of my signal is this much, but the phase is still 0 because in amplitude shifting I don't change the phase. Phase has to remain the same. Okay? So for both these dots, the phase is the same, but the amplitude is changing. For this one, the amplitude is 0, and for this one, the amplitude is something 5 volt or whatever. Right? Okay. There is another example. Look at this one. Binary phase shift key, BPS. What is happening here? For bit 0, I am sending this dot, and for bit 1, I am sending this dot. Right? Now, if you look at these two, this amplitude and this amplitude is the same. It has to be same because it is phase shift key. I should not change the amplitude. Right? But you see the phase is changing. What is the phase for this guy?
100.
No, for this. 0. The phase of this is 0, right? And for the phase for this is, as you said, 180 degrees. Right? So here, just these two dots are telling you that I am using PSK and with the two amplitudes. Right? Now look at this one. This is QPSK. Okay? You can see that all these dots are on a circle, which means that the amplitude of all these dots is same because the circle, any dot on the circle has the same amplitude, right? So the amplitude is same, so it cannot be amplitude shift key. And what about the phase? So you can see that the phase of this guy is this, as I just showed you on this diagram. The phase of this is this, and this, and this, and so on. Right? So you can see from here that even if I have 8 PSK, that is I have 8 different phases. I'm sending 3 bits at a time, then I should have 8 different phases, right? So I can have them, for example, somewhere in between. I can say, okay, this is another dot, this is another, this is another, and this is another. You keep on increasing and you can show them all on the same constellation diagram. Right? Is it clear?
Yes.
Okay. Then the fourth one, we have talked about 3. We talked about ASK, we talked about FSK, and we talked about PSK. No, let him come. Too many people are going for washroom. Yeah. The third one is PSK that we just talked about. Okay. This one is quadrature amplitude modulation. Combination of ASK and PSK, which means that you are changing the amplitude as well as the phase of your carrier signal. So this is what he said. So far we have been altering means changing. So far we have been altering one of the 3 characteristics, that is properties of a sine wave at one time. Okay. What if we change 2 properties of the sine wave at the same time? What if we change 2 properties of the sine wave at the same time, which is amplitude and phase? The idea of changing phase and amplitude of the carrier at the same time is quadrature amplitude modulation, or QAM. Right? And it may look something like this. Look at this one. For this dot, the amplitude is 0 and the phase is 0. For this dot, there is some amplitude. Let's suppose let me give numbers. This is, let's suppose, 1. This is also 1. Right? Okay. Now if I ask you, what is the amplitude of this guy?
1.
Phase?
0.
0. How about this dot? How much is the amplitude?
1. 2.
What is the amplitude of this dot?
Cosine.
Amplitude.
No.
No, amplitude, man. I'm talking about this length. Is this length 0?
It's tan 1.
Sorry, again.
It's tan 1/1. Tan 1.
Tan 1.
Yes.
Yes. Say it loudly.
Pythagoras.
You know what is this theorem?
Yeah.
So what is that? So what is the value of this?
√2.
Yes, very good. So the length of this will be the square root of 1 square plus 1 square. Right? Remember? So what is 1 square? 1. This is 1. Square root of 2. This is what it is. Right? And what is the angle? 45. Okay. How about this dot? The length is
1.
1. Angle is phase 90. So you can see that the phase here is 0. Here is the phase is 0. Here the phase is 45. And here the phase is 90. So the phase is changing. How about the amplitude? Amplitude is also changing. 0, 1, √2, and 1. Right? So that's why this is called QAM. That both phase and amplitude are changing at the same time. Right? Because in ASK only the amplitude changes. In PSK only the phase changes. But in this case, both are changing. This is another example. It's a kind of a square, right? So here as well, although the amplitude is pretty much the same. So let's take another example. See this one. The amplitude of this guy is right? Amplitude. And how about the phase? It's something like 45, right? And this is another one. You see the phase has changed. The amplitude has also changed. For this guy, this is the amplitude and phase, right? And for this guy, this is the amplitude and phase. Right? You want to go to the washroom?
Yes.
Yeah. Okay. Look at this one. This is 16 QA. What's the meaning of 16? I'm sending how many bits at a time?
16.
4.
4 bits. You're sending 4 bits at a time. That's why you have 16 dots, right? Okay. And again, you can see that the phase is also changing and the amplitude is also changing. Right? So is it clear now?
Yes.
How QM looks like? And the bandwidth is the same as PSK and ASK, 1 plus D into S. Okay, now let's solve the problems. Draw the constellation diagram for the following. So he's giving you some situations. Okay, I'll solve the first one and then you'll solve the rest 3. He's giving you some situations and he's saying you draw it just like you saw those dots. Okay, try to draw it as clean as possible. And it should look okay. The phase, the amplitude is changing or phase is changing. So let's take the first example. You draw the constellation diagram of ASK. Okay, keep in mind ASK. ASK means only the amplitude will change. With peak amplitude values of 1 and 3. Okay. What does it mean? That if this is the constellation diagram, this is X, this is Y, okay, and this is my origin. So he's saying that I'm using ASK, and ASK means only the amplitude is changing, and the 2 amplitudes that he's talking about are 1 and 3. Okay. So 1 is going to be somewhere here, for example, right? So 1 point will be here, and the other is 3. So this is 1, 2, and 3 should be somewhere. I have 2 points over. So I say that this distance is 1, and this distance is 3. So I can use 1. For this one I can use for bit 1, and this one I can use for bit 0. This way you have to solve the rest of the 3. Is this clear the way I did? Is it clear? So this way you will PPSK with a peak amplitude of 2. Right? So you draw it just like I draw it.